Hello and welcome to this short video on the Mesolimbic Dopamine system. My name is Professor Phil Newton, and what I hope you're able to do by the end of this short video is just to be able to describe the role of the Mesolimbic Dopamine system in goal-directed behavior. The punchline of this video and what we're going to try and cover is very basically how biological rewards motivate behavior. We are motivated to obtain certain things in our environment, and we make a decision to pursue those rewards at the expense of other options that we might have chosen instead. Let me give you a very simple example. If I were to offer you a choice between some chocolate and some lettuce, most of us would choose the chocolate. Most of us who wouldn't choose the chocolate would mostly do so because we don't like chocolate, not because we prefer lettuce. If I were to change this choice ever so slightly so that you had a fixed amount of chocolate, let's say the amount on the right, and an unlimited amount of lettuce, most of us would still probably choose the chocolate. Chocolate is a highly palatable food, and we have learned that through our experience of eating it. And the same is true of other highly palatable foods. Most of us would choose donuts or other sugary, high palatable foods over things like lettuce or low calorie or low energy density foods. The reason for that, as I said, is because chocolate is a biological reward. The means by which we've learned this involves two key brain regions. The first of these is the midbrain, and you can see it highlighted here in red. It's quite a deep and quite an old brain region. It then projects to another region of the brain called the striatum, in particular the ventral striatum. The midbrain and the ventral striatum are wired into lots of other brain regions, but it's the connection between these two regions that we're going to cover in this video because it more or less is the mesolimbic dopamine system. Let me explain it in a bit more detail. The star of this show is dopamine, neurons making dopamine, and here is a cartoon of one. Every time it fires an action potential, dopamine is released. The cell bodies of these neurons are located in a region of the midbrain called the ventral tegmental area. The axons of these neurons, the terminus of these neurons, is in the striatum, in particular the ventral striatum, specifically a region called the nucleus accumbens. The connection between these two neurons is called the medial forebrain bundle, and between them, these three regions form the mesolimbic dopamine pathway. The ventral tegmental area sends dopaminergic projections to other regions of the brain. A very important one is the prefrontal cortex, and this forms the mesocortical dopamine pathway. In this slide's video, though, we're going to focus on the mesolimbic system, and we're going to start with the medial forebrain bundle, where the axons of these dopamine neurons are carried from the VTA through to the nucleus accumbens. We're starting here because this is largely how the mesolimbic dopamine system was discovered through some very famous old experiments back in 1954 that were looking at intracranial self-stimulation. These experiments were conducted by Olds and Milner. They were quite old-fashioned, but they were seminal in our understanding of how rewards are learned about and how we are motivated to achieve them. Intracranial self-stimulation involved placing stimulating electrodes into regions of the brain, in this case of rats. The rats learned to press a lever to receive that brief electrical stimulation. Olds and Milner were not looking to discover the mesolimbic dopamine system or even really to discover reward, but they discovered it quite by accident when some of their electrodes became misplaced. Specifically, they were placed into the medial forebrain bundle. What they eventually discovered after following their intuition in a series of experiments was that rats would learn to press a lever to receive an electrical self-stimulation directly into the medial forebrain bundle. And once they had done that, then the rats would abandon all other behaviors. They would deprioritize things like eating, sleeping, and drinking, and searching for a mate, and simply focus on pressing the lever. This was a profoundly important discovery because it showed, or at least at the time it was thought that it showed, that we had discovered the pleasure center or the reward center. We now know that it's a little bit more complicated than that, but it's led to a lot of misunderstanding about what dopamine does. Lots of people think that dopamine is the pleasure chemical or the love chemical or the reward chemical or the addiction chemical, and you will see that in popular press presentations of it. Dopamine actually does something slightly more sophisticated and complex. Basically, what dopamine neurons do is they encode reward prediction error. They learn to change their firing pattern in response to a reward, and then they change their firing pattern again if that reward is not delivered. Let me give you a very simple example. Here then is our dopamine neuron. On the left-hand side, you can see a graph over time, and every blue line there is when that neuron fires an action potential and dopamine is released. I'm showing you this to emphasize the point that dopamine neurons show a tonic rate of firing. That is, they are ticking over at any one time, constantly firing at a particular rate. Let's say we encounter something wonderful. This, for those of you outside the UK, is a Whisper chocolate bar, and it is the most delicious chocolate bar that mankind has ever invented. Let's say we are fortunate enough to consume a Whisper. We've never seen a Whisper before, we've never seen the logo before, we've never seen the package before, but we bite into it and it is, of course, delicious, and we are very happy as a result. Because it is delicious, very simply what our dopamine system does is it increases the firing rate of those dopamine neurons. And that is our way of learning about the fact that something delicious has just occurred, something wonderful has just happened. Our dopamine system is basically the way in which we learn about the environmental cues that are associated with that wonderful thing happening, so that we know when it's going to happen again and we can go ahead and achieve it. What happens then is after a few episodes of learning, let's say we eat a few Whispers once a week for a few weeks, eventually what happens then is when we just see the Whisper logo itself, or the thing that we have learned is associated with the wonderful thing happening, that will cause the increase in firing of our dopamine neurons. Basically now dopamine is switched from being this learning signal to a motivation signal. It is saying, look, inside that blue wrapper with the red writing is something wonderful and you need to go ahead and do it. If we see that in the shop or we see it on a billboard, then again, our dopamine system will be activated into firing. Let's say we go ahead and consume a Whisper after we have learned and after dopamine has become this motivation signal. But when we bite into this particular Whisper, it is filled with something disgusting. Let's say Brussels sprouts, which are, of course, the most disgusting vegetable ever eaten. In this case, dopamine is now encoding an error. So dopamine neurons have switched up their firing rate in response to the sign of the signal, got us all motivated, we've eaten the Whisper, and then something delicious has not been delivered. In this particular case where there is an error and we are unhappy, then the firing rate of the dopamine neurons will go down. This will help us then learn that not always is the Whisper logo associated with something wonderful happening. And if, of course, we were to repeatedly eat Whispers, which were then filled with Brussels sprouts and were so not delicious and were disgusting, then eventually we would, if you like, unlearn this association between the Whisper logo and the packaging and something wonderful happening. Just in case you're wondering why we don't just go ahead and consume all wonderful things whenever we see them, that's because of the role of the prefrontal cortex, which has a profound top-down influence over the actions of the mesolimbic dopamine system. But we've covered that in another video, so I won't talk about it so much here. All right, the final slide then is just to cover what goes into and what comes out of the mesolimbic dopamine system. The signals which help us learn that something wonderful is happening come in part from the limbic system and obviously through the other sensory systems into the limbic system. The limbic system is our way of learning how we feel about something, communicating emotions. The prefrontal cortex also has reciprocal connections to the mesolimbic system for reasons I've just discussed. The outputs then of the mesolimbic system, lots of them are motor systems, basically turning up or down the volume on our decision whether or not to enact a particular motor command, in particular through the basal ganglia and a region of the basal ganglia called the ventral pallidum. The basal ganglia are responsible for motor initiation, and so when we're considering initiating a motor movement towards a Whisper or something that we've learned about that is wonderful, the actions of the mesolimbic dopamine system will turn up the volume on that, which makes it more likely that we will choose it. And then there are further projections onto thalamocortical loops, which are very important for regulating all of our behaviors. All right, the summary then of everything that we've covered. Rewards stimulate the release of dopamine. Unexpected rewards are the most potent. When we didn't expect something to be good, dopamine kicks into action to make sure that we learn about it. Dopamine then acts, as I said, like a learning signal so that we learn about the environmental cues which predict that reward. Eventually, those cues themselves are what causes the release of the dopamine. In the example that I gave you, once dopamine had taken on this motivation role, this learning signal role, when we ate the Whisper itself, we would not get that release of dopamine. The dopamine comes from the expectation caused by seeing the cues in the environment which show that it is available. If the reward is not obtained, particularly if that is unexpected, then the firing rate of dopamine neurons goes down. Again, that is acting as a learning signal. The actions of this circuit ensure that we learn about rewards, and you can see an obvious evolutionary advantage to this. If we suddenly came across something palatable, we would want to make sure that we learned about it so that we could do it again. We're highly motivated then to obtain those rewards. And that's another reason, another action of the mesolimbic system is turning up the volume on the choices that we might make in order to obtain those rewards. All right, the references, the two key papers that we've covered here, Alton Milner from 1954, and then the work of Wolfram Schultz, who did a lot of work to decipher the dopamine reward prediction error coding function. And these are the image credits, and again, all images, as always, are used under fair use exemption for teaching. The Whisper picture was all my own work. Any questions, send me an email. That's my email address there, and I'll see you in another video. Bye-bye.